Welcome to solverfy.
This is chapter 27, problem number 2. We have a particle of mass. This is given. The charge is given. It's a charged particle, and it has an initial horizontal velocity that is due north, and the magnitude and direction of the velocity is given. We're asked what the magnitude and direction of the minimum magnetic field that will keep the particle moving in the Earth's gravitational field in the same horizontal northward direction. Well, first of all, for this to happen, we have to have the net force acting on this particle to be zero, meaning if you read the problem, there are two kinds. You can figure out that there are two kinds of forces. One is the gravitational force, and the other one is the magnetic force. So magnetic force then minus gravitational, because they're along the opposite directions. I'm going to draw the diagram. We're going to get a better understanding. It has to be equal to zero, right? This is the condition. From here, the magnetic force acting on the charge has to be equal to the gravitational force acting on the charge, which, by the way, we know what F sub g is, right? It's m times g. Anyways, so what's going on is, let's draw the diagram. North, south, east, west. So the charge, imagine, is at the center. It's going north with the velocity v, right? Which means the gravitational force, then the direction of the gravitational force is actually into the board, right? So we can show it this way. This is the direction of Fg. Now, if that's the case, then the direction of the magnetic force has to be the opposite, right? To balance it out, F sub b. The same statement here, which means Q times the charge of the particle times the velocity times the magnitude of the magnetic field has to be equal to your gravitational force. From here, we can actually easily calculate the magnitude of the magnetic field. So it would be mg over qv. So if we do this calculation here, m, which is 0.195 times 10 to the power of -3 kilograms. We have to do the conversion from grams to kilograms. And then we have the gravitational acceleration, which is 9.8 meters per second square. And in denominator, we have the absolute value of the charge, right? It's you don't take this negative into consideration. You do a negative 2.5 times 10 to the power, this should be -8. My apologies, it's -8. And then coulombs, right? Times, we have the velocity, it's the speed, well, magnitude of velocity vector, which is 4 times 10 to the power of 4 meters per second. So if we do this calculation, we're going to find the magnitude of the magnetic field, V, to be 1.911 Teslas, right? Now, this is the magnitude, but we also need to find the direction of the magnetic field B. Then, in order to do that, we're going to go revisit. We said that the magnetic force should be then out of the page, so it's towards us, towards the screen. So then, if that's the direction of the magnetic force, from the right-hand rule, by aligning, well, everybody has a different way of doing it, but from the right-hand rule, then you can determine that the B has to be actually eastward. Because if B is eastward, look, this is the direction of the B. So then first you align your fingers with the direction of V, then or your thumb with the direction of the V, and then the rest of your fingers are going to go along B. Then you're curling your right hand 90 degrees, which is into the page, right? This is the direction of the F sub B using the right hand rule. However, you have a negative charge, so you have to take the opposite of it. From the right hand rule, it was into the page, and now since it's a negative charge, you're going to take the opposite, so it's going to be out of the force is going to be out of the page, which basically is aligned with what we already said here.